Tuberculosis is a large problem in Uganda. According to TB Online, in 2019 there was around 90,000 infections a year. The problem with the current TB vaccine is that it has variable protection. For example, it's less effective in males. Our challenge is to create a vaccine to treat TB in Uganda. The vaccine will be protein-based and will use a bioreactor to maximize the growth of the yeast cells to create more protein for the vaccine. We will look at reactor conditions to generate highest cell growth by focusing on mixing, heating, and impedance conditions. Our market and product specification. The Ugandan population is 47.7 million. We decided to vaccinate 94%, which is 44.8 million people. We aim quite high in order to reach herd immunity, which is achieved between 70 to 90%. And no matter what, we'll always vaccinate less than planned due to possible transport or logistical issues. TB mostly affects males, as well as young children under 14 years and the elderly over 65. As for the remaining 6% of the population that's unvaccinated, we have considered those who are immunosuppressed as well as those with HIV or AIDS who are not usually vaccinated due to risk associated with the live vaccine. So we will need 89.7 million doses in total. As the Ugandan GDP is quite low, around $817, and the disposable income is $95 per year, minimum wage, we decided to make the vaccine cost $0.78 per dose, equivalent to approximately 0.18% of their GDP. Assuming yeast cell concentration in the bioreactor reaches 50 grams per litre, and of that cell concentration 0.01% is our protein vaccine, and we need 2 doses, we calculated our total bioreactor capacity to be 18,700 litres based on workers working 48 weeks out of 52, giving them 3 weeks holiday per year. So as a benchmark, we used the Imflow manufacturing facility whose bioreactor capacity is 30,000 litres per batch. We then calculated the annual estimate of water to be 4,320,000 litres and the annual electricity requirement to be 1.44 times 10 to the power of 7 watts. Mixing is important as it reduces size of gas bubbles and provides oxygen, whilst maintaining a homogeneous chemical and physical conditions, which creates an optimal environment. The mixing parameters we used were 350 milliliters of water and 5 drops of food colouring. For test number 1, we used 1 hydrofoil impeller. For test number 2, we used 1 hydrofoil impeller and 4 baffles. And for test number 3, we used 1 hydrofoil impeller, 1 paddle, and 4 baffles. We raise the baffles so it doesn't interfere with stirring, and we use paddles as they are gentle and have a low shear agitation, especially in high viscous liquids.
According to studies, optimal agitation speed is between 200 rpm and 300 rpm. This is to avoid cavity formation so cells are not damaged. We used a theoretical mixing equation to get the times for the RPMs and plotted it on a graph. We are expecting similar values for the times on the graph. When the actual results are obtained, we will plot it on a graph.
Here are the objectives for the probe subtask. For our first lab session, we need to find the optimum parameters for the yeast concentration measurements. For our second lab session, we need to calibrate the probe and create a reference curve that can be used during the third lab session to perfect our method, then again for the 24-hour session. The materials we need for the probe subtask is the NI MyDAG, where the wires that go into the solutions of the yeast and PBS, which is then also connected to the laptop, which has the measuring equipment programs such as NI function generator and the NI oscillator, the PBS and the yeast solutions provided, and in addition to an enclosed PCB circuit that is connected to the MyDAG.
Placement of the electrodes, and during the first lab, we alternated the frequency, amplitude gain, and voltage one by one and compared all of the measurements to find the best set of parameters to have a high contrast between the two solutions, so it's as accurate as possible during the 24-hour run. For the second session, we will make several dilutions from the yeast solution with known factors so we can calibrate the probe.
Heating affects cell growth efficiency. Low temperatures can slow down or stop cell growth, and high temperatures will lead to denatured cells. This would greatly affect our vaccine yield. We've chosen 25 to 30 degrees as our optimal temperature range for yeast cell growth. An average temperature within this range will promote an optimal growth rate. The hot plate will be kept at 30 degrees to account for the temperature difference between the base and the top of our bioreactor. Our approach is to measure the temperature change over a set distance. We will test insulation designs first to determine our temperature maintenance method used for the 24-hour session. Then we will test with mixing conditions, which may impact our initial decisions.
The results acquired from these series of experiments can be used to plot a graph which will display the temperature profile under the different conditions, and an analysis of this graph can be used in Fourier's law to calculate the heat flux flow along the vertical axis and radial direction of the plastic cup. We can expect our findings to show that an optimal temperature range can be maintained using 2 to 3 layers of insulation whilst taking into account the apparent heat loss. There will be less variation in temperature between the bottom and the top, so that it will lie within the optimal range for growth of yeast cells, but we can anticipate that this may change when we test with mixing conditions. Interactions between the systems is possible, and this can cause problems with the process of cell growth. This can range from the interference from impellers moving the wires using the impedance probe if the RPM is too high, to the temperature dropping from the optimal range due to unexpected heat loss through mixing. However, this can be negated by following through with the correct precautions, like the positioning of the wires and impellers to avoid interaction in the bioreactor, and setting the temperature at an upper limit to account for further heat loss. Any challenges met during the testing can be dealt with in the same manner.